All right, Chapter 2, Section 8 is Applications of Proportions. So 2.8, Applications of Proportions. And for these, it's going back to stuff that we did in Math 8, so it'll be kind of a nice review. Similar figures. If you have two figures that are similar, basically they look the same, they're just going to be different sizes. So I'm going to say same shape, but maybe different sizes. So same shape, but may be different sizes. So an example then would be pictures of people. That if you have a small picture, your small school picture and your big school picture, your face should look the same in both of them. They're just going to be different sizes. Or another example, you could talk about like the model. When we were kids, my brother made a model of a F-14 Tomcat. If you would measure, say, the wingspan of the plane compared to the length and come up with a ratio, that should be the exact same ratio as the wingspan to the length of a real F-14 Tomcat. Or maybe I should say the model compared to or with the original, that those would be similar figures. Or you could go that first example and say two pictures. So pictures of the same thing that are different sizes. Or the more common one that we are going to look at is going to be two shapes, often triangles. So I'm going to say two triangles with the same angles. So I drew a couple of triangles there and tried to make them look similar. So I tried drawing triangles where the angles are the same. They're pretty close. So I draw two like that if I were you, one larger than the other. And once you get that drawn, I'm going to go ahead and label the vertices or the corners of the different triangles. So this first triangle, I'm just going to put an A on top, a B on the right, and a C on the left. And maybe I'll go with a M and a N and an O for my second one. Now in labeling these triangles, you need to, when you label a figure, pick a spot and go around the figure. You can't jump across diagonally. And that for a triangle you can't jump across. But so for this first triangle you could say it's triangle ABC if you wanted to, starting at the A and just kind of going your way around. You could have started at the C and went the other direction, so you could call it triangle CBA. So C and then B and then A and so on. But if you want to say the two are similar, the little notation for similar is going to be that red thing right there. It's kind of like half of a congruent sign, just kind of one tilde, one little squiggly. But now when I go and label my second triangle, I need to make sure that whatever vertice, whatever corner I put in first, corresponds to this A. So it has to be M, that this angle A and angle M both have that same number of degrees, so I have to say triangle M. And then I did ABC, so I have to do MNO. So triangle MNO. And I did capital letters for the vertices. Usually you'll see them do capitals for the angles or for the corners, the vertices, and then lowercase letters for the sides. If you wanted to go and label that one differently, you could label them, and you could say instead, maybe let's do triangle, well, why not? We'll do CBA for my first triangle, and you could say, well, that's congruent to my second one. I have to start in the same location, so it would be O, and I have to go the same counterclockwise direction, O and M. So that'd be two ways to say that the triangles are congruent. And by being careful of the order that you write them in, you can now know that, then that angle C is congruent to angle O, because they're both listed first. Or you could say angle A is congruent to angle M, or angle B is congruent to angle N, and so on. Okay, from there then, let's say they give us a few different sides. So I'm going to say I know that the sides of my triangles up here, why don't we say this one is going to be a 2, and then this one looks like it's about a 5. And if we say this one here is, why not, we'll just go with a 4. And if we're trying to find this missing side there, because those triangles are similar, we could then set up a proportion like we were doing in section 7. So I can say, all right, in my first triangle, I could say 2 over 5, so that's the ratio of this side to this side. As long as we know they're similar, that should equal the ratio of this side to that side. So 2 over 5 equals 4 over x. And now, just like we did in the section 7 notes, we could go and we could solve for x. You could cross multiply and divide. You could say 2 times x equals 4 times 5, and then divide both sides by 2. But it's probably easier in this case to say, well, okay, to get from 2 to 4, they multiplied by 2. So I could do that same thing in my denominator, and I know that 5 times 2 then gives me 10. So x would just have to be 10 units long. But you could do it cross multiplying and divided if you wanted to. One last section of the notes. And for this last section, I want to just kind of look at what happens as we have similar figures. What happens to the different parts of it? So, or maybe we'll say we have 2 circles. And I'm just going to kind of make this into a chart. So it's going to have 3 columns to it. And my second column is going to be my first circle. We'll say that this circle has a radius of 2. And my third column is going to be my larger circle. We're going to double it. So this next circle has a radius of 4. We have something that's twice as big. And what I'm trying to look at is I'm trying to say, all right, I'm going from these 2 circles. One circle is going to be twice the size of the other circle. So I could do the little arrow and I could say a times 2 right there. Well, now what happens to, first of all, the circumference? Circumference is the distance around a circle. It's going to be 2 times pi times r. And I'm not going to go all the way through and get the decimal answers. Hopefully that doesn't mess you guys up too much. But we could take, if we wanted to figure out the circumference of this circle here, well, we know the radius is 2, so I could substitute the 2 in for my r. And that's going to give me a 2 times pi times 2. Because it's all multiplication, we can switch the order around. So now the circumference then is going to be 2 times pi, or just 4 pi. So approximately 12 point something, because it'd be 4 times the 3.14. If I were to do that same thing for my larger circle, my radius is now 4, so I put a 4 in there, so I get a 2 times 4 times pi. So that gives me the circumference is going to be 8 pi. So you'll notice then, just like we had with the radii, the radius is, you could say plural for radius, radii, that just like the radius was doubled from one to the other, as I go from the circumference, that's also going to be times 2. So far, it probably seems pretty logical to people. But now we want to say, well, what happens to the area? So area, but now we want to say what happens to the area. Area of a circle is pi r squared. So now when I take and look at my first circle, the radius is 2, put a 2 in there, I get pi times 2 squared, or my area is going to be 4 pi. Now as I go and do my second circle, I take and put a 4 in for my radius, and I get 4 squared is 16, so now I have 16 pi. So the strange thing is, now for area, it's not twice as big, it's 4 times as big. Because 4 pi times 4 gets me up to my 16 pi. And so what about the area makes it times 4 when everything else is times 2? And what it ends up being is this squared right here. The reason this ends up being 4 times as large is because what I did is essentially I did this here. I'm going to take and kind of look at my r, I'm going to make that in black. So say my original circle just has a certain radius. Well, now when I take and double that, so say this top equation here, that's going to be the equation for my original circle. If I want to do my new circle, well, it's going to be a equals pi times, instead of just r squared, I now have a 2 times r. It's twice as big, squared. But when we square that, we need to have that 2r in parentheses, because we need to make the radius twice as big before we actually do the problem, before we square it. So you'll remember now that the exponent there applies to everything inside the parentheses. So my new area becomes pi times 2 squared times r squared. And now as I go and finish off my problem, I have pi times 4 times r squared. So you'll notice my equation here is almost identical to the equation above. I have area equals pi r squared, area equals pi r squared. The difference is this times 4 in there. So when you double the radius, because it's radius squared, you don't just double the area, you need to take your 2 squared, and that's going to be how much bigger you make the area. So that's just kind of an intro to it right now. That's going to kind of pop up a little bit later, but just want to show it to you briefly now.